The machines under the streets and avenues we walk across every day pump around 13 million gallons of water out of the subway tunnels. Don't assume they only do this on stormy days. They do it every single day. The tunnels sit below the water table, so those machines are the only thing keeping them dry. If something went wrong and the system shut down, water would start building up within about 36 hours. That is one city, one system, and one detail. But it points at something most people never even consider. The modern world is not a fixed object. It is a process that needs constant maintenance. Now let's run a thought experiment that scientists have actually worked through in detail. Suppose every human being on Earth vanished tomorrow. There was no war and no disaster. There are no bodies and there is no great destruction. All that is left of people are the things they built. What would happen to America? In this documentary, we are going to look for the answer. We will start with the first week and move on to the first year, the first century, and then far longer spans of time. How many years would it take for the land we live on to return to its old wild state? If you are also curious about what would happen where you live after people disappeared, you can subscribe to my channel. Now let's go through what would happen in order. The first thing to go is the lights. Power stations run on a continuous supply of fuel and water, and they need people to keep that supply moving. A coal plant needs coal delivered. A gas plant needs gas flowing and pressure regulated. A nuclear plant needs operators. Within hours, generating stations begin dropping off the grid as their fuel supply fails or as automatic systems shut them down without anybody to respond. It is worth appreciating how tightly coupled that system is. A modern power grid holds supply and demand in balance continuously, second by second, and it is monitored around the clock by people whose entire job is to make small corrections. Nobody notices that work because the correct outcome is that nothing happens. Remove the operators and the corrections stop, but the imbalances do not. Some places stay lit slightly longer than others. Hydroelectric dams keep spinning as long as water keeps flowing through them, and solar panels keep producing as long as the sun rises. But the grid is not a collection of independent lights. It is a single balanced system, and when supply and demand fall out of step, protective systems disconnect sections automatically to prevent damage. Without anybody to reconnect them, the network fragments and goes dark in stages. Most of the continent is unlit within days. The exceptions are worth noting because they are the last visible signs of the world that just ended. Solar arrays keep producing power into circuits that no longer lead anywhere. A handful of self-contained systems with their own generation and storage keep running until something in them fails. Emergency lights burn on battery until the batteries are flat. For a few days, there are scattered points of light across a dark continent, and then those go too. And the moment the power goes, the pumps stop. This is the part of modern infrastructure that is genuinely invisible until it fails. Underground spaces in almost every major city sit below the local water table, which means groundwater is constantly seeping in and being pumped back out. New York's subway system removes 13 million gallons a day just to stay operational. Within about 36 hours of the pump stopping, water begins to accumulate in tunnels and underground car parks, and it does not stop accumulating. Try to picture the quantity involved. 13 million gallons a day is roughly 20 Olympic swimming pools, arriving every single day into a system whose only defense is a set of pumps that have just lost power. The water does not need to break in. It is already there, and it has been arriving continuously the entire time the system has existed. All that changes is that nothing is sending it back out. That process is not unique to New York. Any underground rail system built below the water table faces the same problem, including those in London, Boston, and Washington. The timeline varies with local geology and rainfall, but the mechanism is identical everywhere. Modern underground infrastructure is not naturally dry. It is actively kept dry every day by machines that need people to run them. This is the single most useful idea in this entire account. and it applies to far more than tunnels. A very large proportion of what looks permanent in the built world is actually being held in a particular state against a constant pressure to return to a different one. Dry basements, straight rivers, mown grass, clear roads, functioning bridges. None of these are resting states. They are all positions being maintained. Water in the tunnels is the beginning of a chain that ends much later with the streets above. Water works into cracks in concrete and surrounding rock. It freezes in winter and expands, widening every crack it enters. It corrodes the steel reinforcement inside concrete, and corroding steel swells, which cracks the concrete further from the inside. Within a few years, unmaintained tunnels would begin to see partial ceiling collapses, particularly in older sections dating to the early 1900s. Decades later, that is how streets fall into the ground. And when a street collapses into a flooded tunnel beneath it, the failure is not gradual. The surface holds until it does not, and then a section drops into the void below in a matter of seconds. Cities with extensive underground systems would develop these collapses steadily over the first century, and each one opens a new route for water and weather into the network beneath. Above ground, the first week is mostly quiet. Traffic lights are dark. Refrigeration has stopped everywhere. Water pressure in municipal systems fades as pumping stations lose power and taps stop running. Fires start where they were going to start anyway, from electrical faults and lightning strikes, and nobody puts them out. In dense areas, a single fire can move through a block, and there is no reason for it to stop until it reaches something that will not burn. Modern urban firefighting is so effective that it is easy to forget how catastrophic urban fires used to be. Chicago in 1871, San Francisco in 1906, London in 1666. Entire cities burned because the fire had nothing to stop it. Modern building codes and fire separation would slow it down considerably. But with no suppression at all and no power to run any system, large sections of dense American cities would burn in the first years. The animals that depend most directly on us feel it fastest. Livestock in enclosed facilities are in immediate difficulty because they are entirely dependent on delivered feed and water. Domestic dogs, particularly small breeds, are poorly equipped for a landscape with no human support, though some would survive and larger dogs would do considerably better. Cats do better still, because a domestic cat is a functional predator that has never really stopped being one. Rats and pigeons and cockroaches, which most people assume would inherit the earth, are in fact in serious trouble, because their entire way of life is built on a continuous supply of human food waste that has just ended. Cockroaches are a similar case, and the reason is temperature rather than food. The species that infest buildings in most of North America are tropical animals that survive northern winters only because we heat the spaces they live in. Without heating, cockroach populations in cold regions collapse within a single winter. They persist in the warm South, where they were always going to be fine, but the ones in Chicago apartments are living on borrowed warmth. That last point is worth sitting with because it reverses the usual expectation. Urban rats are not thriving despite us. They are thriving because of us. Remove the food supply and urban rat populations would crash within months, not rise. The animals that inherit the cities are not the ones we associate with cities now. The same logic applies right across the urban ecosystem. Gulls in inland cities live on landfill. Squirrels in parks are supported at unnatural densities by food that people provide, directly or otherwise. A great deal of what looks like wildlife thriving in cities is actually wildlife being subsidized by cities. And when the subsidy ends, those populations fall back toward what the land can support on its own, which is considerably less. By the end of the first week, then, the continent is dark, quiet, and still standing. Nothing has visibly collapsed. Every building is exactly where it was. The change so far is almost entirely invisible, happening in tunnels and basements and inside the walls of things. And that is the pattern for everything that follows. The damage begins in places nobody is looking, long before anything falls down. Within the first year, the difference becomes visible, and it starts with water getting into places it was never allowed to reach. A building is essentially a machine for keeping weather out, and its most important component is the roof. Roofs fail at their weakest points, around drains that are now blocked with leaves, at flashing that has come loose, at membrane seams that have opened in the sun. Once water gets through the roof, the building is on a clock. Flat roofs fail fastest, which is unfortunate because they are the standard on commercial and industrial buildings. A flat roof depends entirely on drainage, and drains block with leaves and debris within a single autumn. Water then ponds on the surface, and standing water finds every weakness in a membrane and works at it continuously. A pitched residential roof sheds water passively, which is why houses last a little longer than warehouses do. In humid regions, the interiors go first. Drywall absorbs moisture, mold spreads across walls and ceilings within weeks, and the paper facing on the board begins to break down. Wooden framing takes up water and provides an ideal environment for the fungi that cause rot. Insulation becomes saturated and stops working. None of this is visible from outside, and a house can be structurally compromised while still looking perfectly ordinary from the street. That gap between appearance and condition runs through this entire subject. For the first decade or two, an abandoned American neighborhood would photograph almost normally. The houses stand, the roofs are on, the windows are intact. Everything that matters is happening inside the walls, in the roof space, and under the floors invisibly. And by the time the exterior starts to show it, the structure is already past saving. Outside, the plants get to work, and the first ones do not look like much. Moss and lichen colonize concrete and asphalt surfaces, particularly on the shaded north sides of buildings and in the joints of paving. They hold moisture against the surface, which accelerates weathering. Seeds blow into cracks in pavement and germinate. Grasses establish first because their root systems are dense and shallow and require very little soil to get started. There is a hierarchy to this, and it is remarkably consistent. Lichen needs no soil at all and can colonize bare rock or concrete directly, and it produces weak acids that slowly etch the surface it sits on. Moss needs a trace of accumulated grit and moisture. Grass needs a few millimeters of material. Each one prepares the ground for the next, and the whole sequence can run in a crack in a parking lot no wider than a pencil. Then the mechanism that will eventually destroy every road in America begins, and it is the same one that destroys the subway tunnels: freeze and thaw. Water enters a crack, freezes, and expands by roughly 9%. That expansion widens the crack. In spring, the ice melts and more water enters the larger space, and the following winter the process repeats on a bigger scale. Roads are maintained continuously against this. Without maintenance, a paved surface in a climate with hard winters degrades noticeably within a few years. Anyone living in a northern state already sees this every spring. Potholes are not a sign of poor construction. They are the annual output of a natural process that road crews spend the rest of the year reversing. Stop the crews and the same process runs uninterrupted, cumulatively, for as long as it takes. Within 20 or 30 years, a northern highway is a broken surface, with vegetation established through it. Plant roots do the same job by different means. A root finds a crack, grows into it, and thickens. The pressure a growing root can exert is considerable, more than enough to lift and split concrete over time. Anyone who has seen a tree root buckle, a sidewalk, has watched this happening at the ordinary human pace. Multiply that across an entire road network with nobody repairing anything, and the surfaces begin coming apart within a decade. Concrete and asphalt behave differently in an interesting way. Asphalt is flexible and self-heals slightly in hot weather, but it oxidizes, becomes brittle, and cracks progressively. Concrete is rigid and resists surface wear far better, but once it cracks, the damage is permanent, and water gets straight to any reinforcement inside. In the long run, the concrete lasts longer, but the asphalt fails more gracefully. The lawns are the fastest visible change. American residential landscapes are almost entirely artificial and require continuous intervention. mowing, watering, feeding, and removal of anything that arrives uninvited. Stop all of that, and within a single growing season, lawns return to rough meadow. Within a few years, native shrubs and pioneer trees establish. In much of the eastern United States, the natural condition of the land is forest, and the process of returning to forest begins immediately and moves fast. There is a specific irony in suburban landscaping that is worth noting. Enormous effort goes into preventing exactly this. Herbicides to stop broadleaf plants, regular cutting to prevent anything from setting seed, edging to stop encroachment from the margins. All of that effort is a continuous action against a landscape that is trying, every single season, to become woodland. The moment the effort stops, the landscape resumes what it was doing. Agriculture unravels at a similar speed, but in a stranger way. Modern crop plants are highly domesticated and largely unable to compete without human protection. Fields of corn and wheat produce one final unharvested crop, and are then overtaken within a season or two by wild plants that have been kept out by machinery and chemicals. Irrigation stops, so farmland in the arid West reverts to dry country quickly. Livestock that escape confinement do variably. Cattle would struggle in many areas, but pigs would do extremely well, and feral pigs are already one of the most successful large animals in the American landscape. Domestic crops offer a further curiosity. Modern maize cannot disperse its own seeds at all. The cob holds the kernels tightly and does not shatter, which is precisely what farmers selected for, and it means a corn plant cannot reproduce without someone to strip and scatter the grain. Modern maize would disappear from the landscape within a very small number of seasons. A plant grown across millions of acres is entirely incapable of surviving without us. There is one other event in the first year that deserves mention, and it concerns the places that were being actively contained. Nuclear plants shut down automatically when the grid fails, but reactor cores continue to generate decay heat and require cooling. Backup generators run until their fuel is exhausted. What happens after that depends heavily on the specific plant and its design, and the outcomes range from safe cold shutdown to serious localized contamination. This is the most genuinely uncertain part of the whole scenario, and it is worth being honest that the range of expert opinion on it is wide. But the important thing about the first year is how quickly the invisible becomes visible. At the end of week 1, everything looked normal. At the end of year 1, the grass is waist-high in the suburbs. The roads have weeds in them. Mold has taken the interior of every damp building, and the process that will eventually flatten every structure on this continent is already well underway. Here is where the account stops being speculation, because we have somewhere to look. In 1986, the Chernobyl nuclear plant in what is now Ukraine exploded, and roughly 350,000 people were evacuated from the surrounding area. What was left behind is an exclusion zone of over 4,000 square kilometers, an area about the size of Yosemite, that has been almost entirely without permanent human presence for nearly 40 years. It is an accidental experiment, and there is nothing else like it. Ecologists cannot ethically clear people out of a region to see what happens, and no comparable area exists anywhere else at that scale with that duration and that level of documentation. Whatever else Chernobyl was, it produced the only large-scale, long-running, real-world test of what happens to a landscape when human beings simply leave it. The expectation at the time was that radiation would make the zone biologically dead. That is not what happened. Wildlife populations inside the exclusion zone have grown substantially, and the roster is remarkable. Wolves, lynx, moose, red deer, wild boar, golden eagles, European bison, and Przeworski's horses that were introduced and have established. Brown bears have returned to a region where they had been absent for over a century. The Przeworski's horses are a particularly striking detail. This is a genuinely wild horse species that was extinct in the wild worldwide, surviving only in captivity, and a small number were released into the zone in the 1990s. They established, bred, and spread. A species that had nowhere left to live found a home in an area abandoned because it was too contaminated for people. The conclusion that ecologists have drawn from this is uncomfortable and important. Radiation is genuinely harmful to individual animals, and researchers have documented real effects. But the removal of humans was, for these populations, a larger benefit than the radiation was a cost. That does not mean radiation is harmless. It means that ordinary human presence, through hunting, agriculture, roads, development, and disturbance, applies more pressure to large wildlife than one of the worst nuclear accidents in history. Researchers who work there are careful about how this is stated, and it is worth being equally careful. The finding is not that radiation is good for animals, and it is not that the accident was in any sense beneficial. It is a comparison of two negative pressures in which one turns out to be much larger than the other, and the surprising part is which one that is. So Chernobyl is our best working model, and it tells us what to expect. The animals that inherit an abandoned American landscape are not exotic. They are the ones already living at the edges, white-tailed deer which are already at very high densities across much of the country, coyotes which have expanded across the entire continent and are already established in every major American city, mostly unnoticed, raccoons which are already thoroughly urban, foxes, black bears which would move steadily into suburbs and then into city centers. The reason these particular animals inherit the landscape is that they have already passed the hardest test. Every one of them has spent the last century adapting to constant human presence, which means they are flexible, tolerant of disturbance, dietary generalists, and comfortable in fragmented habitat. When the humans go, the animals best positioned to take the space are the ones that had already learned to live in it while we were still there. Feral pigs deserve their own mention because they are the most consequential. Pigs escaped from agriculture are already among the most destructive and successful large animals in North America. They breed extremely fast, they eat almost anything, and they are highly intelligent. In a continent with no human control at all, feral pigs would expand explosively. The numbers behind that are worth stating. A feral sow can produce 2 litters in a year, with several young in each, and the young reach breeding age within months. That reproductive rate is far outside anything else at that body size in North America, and it is exactly why control efforts struggle even now with enormous resources applied. Remove the control entirely, and the population expands until it hits an ecological limit rather than a human one. And then the predators follow because they always do. Coyotes are already there. Wolves would expand south and east out of their current ranges over decades. Mountain lions, which historically occupied nearly the whole continent and are now confined mainly to the west, would spread back east into the enormous forests that used to be suburbs. Within a century or two, the predator community of the eastern United States would look more like it did 400 years ago than like it does now. And once large predators are back at natural densities, the whole system changes shape. Deer populations, currently far above historical levels in much of the country, would come down. Browsing pressure on forest understory would fall, which changes which tree species regenerate successfully. The animals do not simply return to an empty landscape. They rebuild the landscape into something different by being present in it. It is worth noting what would not come back, though, because the eastern forest of 400 years ago had residents that no longer exist anywhere. There would be no passenger pigeons, no Carolina parakeets, and no American chestnut in the canopy where it was once one of the dominant trees. The forest that returns would be structurally similar and biologically different missing species that cannot be restored by simply removing people. Inside the cities themselves, the early colonists are the species that were already using the built environment as habitat. Pigeons and starlings and sparrows nesting on ledges, which are effectively artificial cliffs, bats in attics, raccoons and opossums in every roof space, peregrine falcons hunting from tall buildings, which they already do. The difference is that nobody removes them anymore, and the buildings begin to change into something closer to natural rock formations as they weather. That is not a metaphor. A weathered concrete structure, with vegetation established on its ledges, soil accumulating in its horizontal surfaces and water running down its faces in the same channels every time it rains, is functionally a cliff. The animals that use it are the animals that use cliffs, and they were using it that way already, which is why peregrine falcons nest on skyscrapers now. The losers are the species most tightly bound to us. Urban rats collapse without food waste. Pigeon populations fall sharply once nobody is dropping food, though a reduced population persists on seeds and natural forage. Domestic animals sort themselves quickly into those that can function without us and those that cannot, and a handful of species that exist only in cultivation or captivity would simply end. What emerges from all of this is a landscape that would be recognizable to somebody from the 17th century, and it arrives faster than most people expect. Within 50 to 100 years, the eastern United States is largely forest with a dense large animal community in it, and the cities are ruins standing inside that forest with animals living in them. That is not a distant future. That is well within the span of a single family's memory. And parts of it are visible now, without any thought experiment at all. Detroit lost a very large share of its population over several decades, and in some neighborhoods the houses have gone and been replaced by young woodland with street grids still running through it. Nobody planned that and nobody built it. It is simply what happens to a residential landscape when the maintenance stops, running at full speed in an American city at this moment. Now the buildings start coming down, and they do it in a predictable order determined almost entirely by what they are made of. Wood goes first. The great majority of American residential housing is timber frame, and wood is organic material that rots when it stays wet. Once a roof fails and water enters the structure, the framing begins to lose strength within a few years and continues to weaken from then on. A wooden house with a failed roof typically becomes structurally unsound within a couple of decades and collapses within 50 to 100 years, often helped along by a heavy snow load or a storm that brings a tree down onto it. The final collapse is usually sudden and usually seasonal. A roof structure weakened by 15 years of rot holds through most conditions and then fails under the first genuinely heavy wet snowfall, or when a large branch comes down in a summer storm. Once the roof is in the building, the walls have nothing bracing them at the top, and the structure comes apart quickly from there. Even creosote-treated telephone poles, which are specifically engineered to resist rot, are unlikely to last more than about 20 years standing in the ground. So the first thing to go is the suburbs, which is not the answer most people expect. The image of a post-human world is usually a ruined city skyline, but skyscrapers are made of steel and concrete, and they last far longer than a house does. The residential neighborhoods that cover the vast majority of developed American land would be gone, absorbed into forest, while the downtown cores were still standing. That inversion is worth holding onto because it changes the picture completely. Developed America is overwhelmingly low-rise and timber-framed. Suburbs, small towns, strip development, farm buildings. All of that is gone within a century. The dense concrete and steel cores of major cities, which occupy a tiny fraction of the total developed area, are what remain standing, as isolated clusters of ruins in an otherwise unbroken landscape. Steel and concrete last longer, but they have a specific vulnerability that is worth understanding, because it explains almost everything about modern ruins. Reinforced concrete is concrete with steel bars inside it, and it works because concrete is strong in compression while steel is strong in tension. But steel rusts, and rust occupies more volume than the metal it came from. When the reinforcement inside a concrete beam corrodes, it expands, and that expansion cracks the concrete from the inside and pushes it off in sheets. This is called spalling, and once it starts, More water reaches more steel and the process accelerates. That is why modern reinforced structures do not weather gracefully the way old masonry does. A Roman aqueduct built from stone and unreinforced concrete is still standing after 2,000 years. A 20th century concrete bridge, with steel inside it, is unlikely to be standing in 300. The very thing that makes modern concrete strong is what makes it perishable. Coastal and northern structures fail fastest for the same underlying reason. Salt, whether from sea spray or from road de-icing, penetrates concrete and dramatically accelerates the corrosion of the steel inside it. A parking structure in a northern city that is salted every winter is already fighting this now, which is why they require constant repair. Without repair, coastal and northern concrete has a substantially shorter life than the same structure in a dry inland climate. Bridges fail early relative to their apparent solidity. They are exposed on all sides. They carry their own enormous weight continuously. They flex in wind, and in cold regions they are salted, which accelerates corrosion enormously. Bridges do not fail because they were badly built. They fail because nobody tightens the bolts anymore, nobody replaces corroded members, and nobody repaints the steel. Within a century or two, most of the bridges in America would be down. Suspension bridges are an interesting case because they fail in a specific way. The main cables are bundles of thousands of individual steel wires, protected from moisture by wrapping and by continuous dehumidification systems in modern examples. Once that protection fails, the wires corrode from the inside of the bundle, where nobody could see it even if there were anybody to look. The bridge holds until enough individual wires have failed, and then it does not. Dams are a category of their own, and their failure changes landscapes rather than just removing structures. Without operators, gates are not adjusted and spillways clog with debris. Water rises behind the dam until it overtops the structure or finds a way around it, and once water is flowing over an earthen embankment, it cuts down through it very quickly. When a large dam fails, an entire reservoir is released downstream, which reshapes the river valley below and returns the river to something like its original course. Most of the artificial lakes in the United States would drain out over the first century or two. Concrete arch dams in narrow canyons are the most durable and would hold longest, but even those depend on outlet works and spillways that clog. Earthen embankment dams, which are the great majority by number, fail much sooner. When they go, the released water scours a new channel through the sediment that has accumulated behind the dam, and within a few decades, the river below looks natural again, running through a valley that has a strangely flat floor where a reservoir used to be. Glass fails on a shorter timescale than people assume, though the material itself is remarkably durable. The problem is not the glass, but everything around it. Seals perish, frames corrode and distort, and buildings shift as their structures degrade. Wind pressure and thermal cycling do the rest. Within a few decades, most windows in tall buildings are gone, and once the weather is inside a building, it works on the interior the same way it works on a house. Put all of that together and the trajectory is clear. Within 100 years, the suburbs are forest and the cities are skeletal. Within 200 to 300 years, most large structures have come down. And what stands longest is not what most people would guess. Not the tallest or most impressive buildings, but the heaviest, simplest, least reinforced ones, buried structures, and anything cut from solid stone. Underground structures do particularly well, which is counterintuitive. Subway stations, deep foundations, buried utility vaults, mines and bunkers are protected from freeze-thaw cycling, from wind, from fire, and from the temperature swings that destroy surface structures. They fill with water and sediment and are then effectively sealed. Long after every building above ground is gone, the shapes cut into the ground beneath them remain. Archaeology already works this way. Almost everything known about ancient settlements comes from what was below ground level: foundations, post holes, wells, drains, pits, and cellars. The standing parts of ancient buildings are almost always gone. A future investigation of American cities would find the same thing, and the plan of a city would be readable from its foundations long after nothing vertical survived anywhere. By 500 years, according to the most detailed treatment of this question, residential neighborhoods have become forest. Not scrubland with ruins in it, but functioning mature woodland with a canopy and an understory and a soil layer that has developed on top of what used to be lawns and driveways. The process by which that happens is called succession, and it runs in a predictable sequence. Grasses and fast-growing herbaceous plants first, because they establish in almost nothing. Then shrubs and pioneer trees, which in the eastern United States means species like birch, poplar, and pine that grow fast, tolerate poor soil, and produce enormous quantities of wind-blown seed. Those first trees create shade and drop leaf litter, which builds soil. In the shade beneath them, slower growing and longer-lived species like oak, maple, and hickory establish and eventually overtop and replace them. That whole sequence takes somewhere between 1 and 2 centuries to reach mature forest, and it is happening right now in parts of America. Large areas of New England were almost entirely cleared for farming in the 1800s and have since been abandoned as agriculture moved west. Those areas are now forest again, and you can still find the stone walls that mark the field boundaries running through mature woodland. That is the process, already documented at full scale, within recorded history. The scale of that reforestation is genuinely surprising to most people. Some New England states were reduced to a small fraction of forest cover in the 1800s and are now majority forest again. Nobody planted most of it. Farms were abandoned as the soil gave out and better land opened up further west, and the forest simply returned on its own over the following century and a half. The thought experiment in this documentary has already run, on real ground, at state scale. Cities take longer because they start from a harder surface, but they get there. The mechanism is soil accumulation. Dust blows in and settles. Leaves fall and rot. Plants grow and die and add organic matter. Each layer holds a little more moisture and supports slightly larger plants. Within decades, streets have a soil layer in the gutters and along the edges. Within a century or two, there is enough substrate for trees. And once trees are established in the streets, their roots accelerate the destruction of everything beneath them. Buildings become forest too, from the top down. Soil accumulates on flat roofs and in gutters. Seeds arrive on the wind and in bird droppings. Small trees establish in roof gardens that nobody planted, and their roots work down into the structure while their weight adds load to a slab that is already deteriorating. Some of the most striking images from abandoned buildings anywhere in the world are of mature trees growing out of upper floors. There is a good comparison available for what that looks like when it is finished, and it is not hypothetical. At Angkor in Cambodia, an enormous stone city built between the 9th and 15th centuries was gradually abandoned and absorbed by tropical forest. Trees grew directly on top of the stone structures, their roots wrapping over walls and eventually holding some of them together while destroying others. When it was documented again in the 19th century, it was a forest with a city inside it rather than a city with trees in it. American cities would end up similar in principle, though the climate makes a substantial difference. In the humid east, the outcome is dense forest, and it arrives quickly. In the arid southwest, structures last considerably longer because there is far less water to drive decay, but they are worked on by wind-blown sand and by extreme temperature cycling, and the vegetation that eventually covers them is sparse. Las Vegas would be recognizable as a ruin for much longer than Atlanta would. That contrast holds across the continent. The humid southeast is the fastest to disappear entirely because heat and moisture drive both decay and plant growth at maximum rate. The Pacific Northwest is similar, with the addition of extremely aggressive moss and fern colonization. The northern plains are slower, held back by cold and lower rainfall. The desert southwest is slowest of all, and structures there would remain visibly artificial for many centuries after eastern cities had vanished into forest. The rivers change too, and this is one of the less obvious transformations. American rivers are heavily engineered, channelized, leveed, dammed, and diverted. Without maintenance, levees breach, channels silt up, and rivers return to their natural behavior, which is to wander across their floodplains and to flood regularly. Many American cities are built on floodplains behind engineered defenses. Those cities would be underwater periodically within decades, which accelerates everything else. A flood through a ruined city does something particular. It moves material. Sediment is deposited inside buildings and across streets, sometimes to a depth of several feet in a single event. That sediment is what eventually buries the remains, and burial is what allows anything to be preserved at all. The cities that survive longest in the geological record are not the ones that lasted longest standing. They are the ones that got covered. Pompeii is the reference case for that principle, and it is worth naming because it is so widely known. That city survives in extraordinary detail, not because it was well built, but because it was buried rapidly and completely, sealed from oxygen and weather in a single event. Almost everything we know in fine detail about the ancient world comes from places that were covered quickly rather than places that stood for a long time. Coastal cities have a further problem, which is that they are at sea level and sea level is currently rising. Whatever the eventual figures, coastal ruins would be progressively drowned, and drowned structures behave differently from dry ones. Some parts corrode much faster in salt water. Others become substrate for marine life and are gradually cemented into reef-like structures. A drowned coastal city does not so much fall down as get built over. Warm water coastal ruins in particular become substrate for coral and shellfish, and marine organisms cement the surfaces they colonize. Structures that would have corroded away in air can be encased and preserved. It is entirely plausible that the longest-lasting recognizable remains of some American coastal cities would be underwater, embedded in reef, several miles from what is now the shoreline. By 1,000 years, then, the continent has an unusual appearance. It is forest and grassland with a full complement of large animals, and scattered through it are geometric shapes, mounds where buildings collapsed, straight lines where roads used to be, rectangular depressions where basements were. From the ground it looks like wilderness. From above, in the right light, the pattern is still visible. Now the timescales change and the ordinary intuitions stop working. Everything so far has happened within a span a human being can conceive of. Centuries, roughly the age of the United States. What follows is measured in tens and hundreds of thousands of years, and eventually in millions. The single most durable large structure in America is almost certainly Mount Rushmore, and the reason is that it is not a structure at all. It is a carving in a granite batholith, an enormous mass of igneous rock, and granite erodes at approximately 1 inch every 10,000 years. At that rate, the carved faces would remain recognizable for hundreds of thousands of years. One frequently cited estimate puts meaningful survival of the monument at over 7 million years, barring a catastrophic geological event. That figure is worth pausing on. Every skyscraper in America is gone within a few centuries. The pyramids of Egypt, which are the most durable large structures anybody has built, are given tens of thousands of years. And 4 faces carved into a South Dakota mountain outlast all of it by orders of magnitude, not because of engineering, but because somebody chose to carve into extremely hard rock in a geologically stable place. The general principle behind that is worth extracting, because it applies to everything. Durability in deep time has almost nothing to do with how impressive something is, and almost everything to do with 3 things: what it is made of, whether the surrounding geology is stable, and whether it escapes physical destruction. A monument made of the hardest available material in the quietest available place beats a far greater engineering achievement made of steel in an active landscape. Beyond that, the surface record gets thin quickly. 10,000 years from now, there is essentially nothing standing anywhere. What exists is a landscape with subtle anomalies in it, unnaturally straight lines in vegetation where roads compacted the soil, mounds of rubble where cities were, unusual concentrations of certain materials in the ground. Archaeologists would recognize it immediately if there were any. From a distance, it is simply landscape. Some of those anomalies would persist for a surprisingly long time. Compacted road beds change drainage and soil density, which affects what grows there, and vegetation lines can outlast the road itself by a very long margin. Aerial photography already detects buried archaeological features this way through crop marks, where plants grow differently over buried walls and ditches. The pattern of American development would remain faintly legible in vegetation long after nothing was standing. And then the ice comes back. The Earth has been in a repeating pattern of glacial and interglacial periods for the last 2.5 million years, and we are currently in an interglacial. The natural expectation, leaving aside current climate change, is that ice sheets return eventually. When they do, they behave like enormous grinding machines. They scour down through soil and rock, carrying everything with them, and they deposit the debris elsewhere. Anywhere that has been under a continental ice sheet has been effectively scraped clean. It is worth stressing how thoroughly that works. The Canadian Shield, which spent repeated glacial periods under kilometers of ice, is bare rock across enormous areas because the ice took everything above it away. This is not erosion in the ordinary sense of gradual wear. It is the removal of the surface, complete and to depth, over an area larger than most continents. That means the northern United States, which was under ice as recently as 20,000 years ago, would be under ice again, and everything on the surface would be removed. Boston, Chicago, Detroit, Minneapolis, and everything between them would not simply decay. They would be ground into a layer of mixed debris and pushed south. And that debris is itself a record of a kind. Glacial till, the mixed material an ice sheet deposits when it retreats, is full of fragments carried from far away. A future ice sheet crossing the northern United States would produce till containing concrete fragments, glass, ceramics, and corroded metal, deposited hundreds of miles from where those materials originated, mixed into ordinary rock debris. Somebody examining it would find manufactured material scattered through it with no source anywhere nearby. There is one further category worth mentioning, and it is the only part of this account that escapes the Earth entirely. The spacecraft left on the Moon and the objects sent out of the solar system sit in environments with no weather, no water, no oxygen, and no tectonic activity. The equipment on the lunar surface is likely to remain physically recognizable for millions of years, long after everything on this planet has been erased. The most durable things people have made are not on Earth. So what survives deep time is not what is standing but what is buried, and the material that survives is not what most people expect. Not steel, which corrodes. Not most metals, which do the same. Not paper or wood or anything organic. What lasts is glass, certain ceramics, and gold and platinum, all of which are chemically stable and essentially inert. A glass bottle buried in stable sediment away from tectonic activity has a genuinely remarkable chance of outlasting almost everything else humans have made. Landfills turn out to be, in this sense, the most successful preservation strategy anyone ever accidentally invented. They bury enormous quantities of material rapidly, seal it away from oxygen and weather, and compress it. Material excavated from old landfills is often remarkably intact, including paper that should have rotted decades ago. If anything from this period survives to be found in a legible state, a landfill is where it will be. There is an irony in that which deserves stating plainly. Our most sophisticated achievements are our least durable. All digital information vanishes within decades without maintenance. Every book decays, every photograph fades. What survives is our rubbish: a stainless steel spoon, a shard of green glass, a fragment of ceramic tile, and a layer of plastic dust. The most advanced civilization in the history of this planet would be represented, in deep time, primarily by its waste. And at the very far end, the numbers become genuinely absurd. Over 1 billion years, plate tectonics would recycle the crust itself. The rock containing any trace of us would be subducted, melted and returned to the mantle. Even Mount Rushmore's granite would be eroded to sand and carried away. On that timescale, the Earth simply erases us. But long before that, there is one thing that would remain legible, and it is not a monument. It is a line. Geologists read the past in layers. Sediment accumulates, gets compressed into rock, and each layer records the conditions of the time in which it formed. A geologist millions of years from now, examining rock formed during our period, would find something unlike anything else in the entire record. The first thing they would notice is the plastic. Humanity has produced an enormous quantity of synthetic polymers, essentially all of it since the 1950s, and a substantial proportion of it has ended up in the ocean, where it breaks down into progressively smaller fragments and settles into seafloor sediment. That produces a global layer of microplastic in marine mud that has no natural equivalent whatsoever. Geologists have a term for objects of this kind, technofossils, meaning traces of manufactured things preserved in rock. The honest position on plastic is that nobody actually knows how long it lasts, and researchers working on this say so directly. The material has only existed since the early 1900s, which is far too short a period to observe its long-term behavior. Experiments can accelerate conditions with heat and ultraviolet light, but most plastic in the world is simply sitting outside in ordinary conditions, and its real fate over 10,000 years is genuinely unknown. The second thing is the concrete. There are now more than 500 billion tons of concrete on this planet, most of it produced since 1950. Averaged across the entire surface of the Earth, that works out at roughly a kilogram of concrete per square meter, over the whole planet including the oceans. Concrete contains minerals that are rare in nature, produced by baking limestone at industrial temperatures, and buried fragments of it will persist in sedimentary rock for millions of years as recognizable anomalies. There is a related material worth mentioning because it is so mundane. Graphite, the material in an ordinary pencil, is one of the most chemically stable substances people routinely handle, and researchers studying this subject have noted that pencil marks could in principle persist for extraordinary spans of time. Our digital records would be unreadable within decades. A pencil line might outlast the continent it was drawn on. The third is chemical rather than physical, and it may be the most informative. Our period shows a sudden spike in atmospheric carbon that is legible in the chemistry of rocks and ice. It shows the largest disruption of the global nitrogen cycle in something like 2.5 billion years, caused by industrial fertilizer production. It shows radioactive isotopes deposited globally in the mid-20th century by atmospheric nuclear testing, which appear simultaneously in sediments worldwide. Any one of these would be an unusual signal. Together, they are unmistakable. The isotope signal is the sharpest of all of them, and it functions almost as a dated stamp. Atmospheric nuclear testing in the mid-20th century distributed specific radioactive isotopes across the entire planet within a few years, and they appear simultaneously in sediments, ice cores, and tree rings worldwide. That is exactly the kind of instantaneous global marker that geologists use to correlate rock layers between continents, and it will remain detectable for a very long time. The fourth is biological, and it is strange in a different way. The rock would record the sudden, simultaneous, worldwide appearance of a small number of species in places where they had never existed. The bones of pigs, cattle, chickens, and rats turning up on every continent and on remote islands at essentially the same instant, geologically speaking. At the same moment, it records an unusually rapid disappearance of a great many other species. Both patterns appear in the same thin band of rock. That combination is what makes the signal so peculiar. A mass extinction on its own appears several times in the geological record and is not unusual. A sudden global redistribution of species is not something the record contains at all. Finding both together, in the same instant, alongside synthetic materials and industrial isotopes, describes something that has no precedent anywhere in 4 billion years of rock. So the layer is unmistakable, and it is worth being precise about what it would look like. It would not be thick. Compressed into rock, everything from the beginning of the industrial period to now would be a band perhaps a few centimeters deep, and possibly considerably less. A geologist would run a thumbnail across it in a matter of seconds. That thinness is a consequence of arithmetic rather than significance. Sediment accumulates slowly, and a few hundred years produces very little rock anywhere. The entire industrial period is a rounding error against the spans that produce visible rock formations. Everything in this account, the whole of modern civilization, occupies a slice of geological time so narrow that it registers as a single event rather than a period. That is the honest answer to the question this documentary asks. Not a ruined skyline, not a monument, not a message. A dark line a few centimeters thick, full of anomalies, running through rock that is otherwise ordinary. It would be immediately recognizable as an event, in the same way that the boundary layer marking the end of the dinosaurs is immediately recognizable as an event. And like that layer, it would be read as something that happened rather than as something that was built. There is something clarifying about that rather than depressing, and it is worth saying so directly. The exercise is not really about the end of anything. It is a way of measuring how much of what surrounds us is maintained rather than permanent, and the answer turns out to be almost all of it. The roads, the buildings, the fields, the lawns, the dry tunnels, the managed rivers. None of these are the natural state of this continent. They are the result of continuous effort, and they are only there for as long as that effort continues. Once you see it, it becomes difficult to unsee. Every time you drive over a bridge, somebody inspected it. Every dry basement is dry because a pump ran. Every clear road was cleared. Every field of crops exists because a landscape that wants to be forest is being prevented from becoming one, this season and every season. None of it announces itself, and the entire measure of its success is that nothing happens. Which is also, quietly, an argument for how impressive the present is. Everything you can see from where you are sitting is being actively held in place. And the people doing it are almost entirely invisible in the way we talk about the modern world. The pump technicians, the bridge inspectors, the line crews, the water treatment operators, the road maintenance teams. Their work never appears in any account of what makes a country function, precisely because when it is done correctly, there is nothing to report. This thought experiment is one of the few ways to make that labor visible, by removing it and watching what happens. That takes an enormous, invisible, continuous amount of work by an enormous number of people, and it has produced a landscape that would not exist for a single decade without them. The thought experiment does not really reveal how fragile the world is. It reveals how much is being done, all the time, to keep it the way it is. Here is roughly how it plays out over time. First, the tunnels fill with water within 36 hours. Lawns and mown grass go back to their natural state within a year and turn into rough meadow. Wooden houses collapse within about 50 years on average. Bridges and towers need 2 or 3 centuries to come down. Neighborhoods outside the cities take 500 years to become forest. The last recognizable structures take around 10,000 years to disappear, except for the 4 faces carved into granite in South Dakota, which could take 7 million. And after all of that, what remains is a thin layer between sedimentary rocks, full of plastic, concrete, and strange materials. There is one detail here that stands out. Some of what I have described is already happening right now. In New England, where there used to be farms, stone walls run through the forests today. In the exclusion zone in Ukraine that people abandoned 40 years ago, wolves, bears, and bison are living now. In Detroit, some neighborhoods have already turned into woodland. And nothing has to end for this process to begin. Somebody simply has to stop maintaining a place, and it starts at that moment. Now I want to ask you something. Is there an old structure near where you live that nobody looks after anymore? And how many years do you think it would take for your streets to turn into forest?